Have you ever stopped to think about just how, well, magical modern technology feels?
It really does seem that way sometimes, doesn't it?
Yeah, like you tap an icon on your phone,
Yeah.
right? And instantly a smart light across the room just responds. Or you're streaming a movie, gigabytes of data just flowing flawlessly to your screen.
hmm Or getting those real-time weather updates.
Yeah.
Just feels like they appear out of thin air.
Exactly. It all feels so effortless, so perfectly, orchestrated. We're interacting with devices, with data constantly. But how often do we really stop and think about what's actually happening under the surface?
That's the question, isn't it? What's bridging that gap?
Right. What incredible engineering is actually spanning that huge, often kind of messy chasm between the pure digital bits and bytes and the physical world, the tangible stuff.
The often unpredictable physical world, yeah.
Yeah. And there's often this deep, almost invisible gap in how we generally understand it all, don't you think?
I think that's fair. We've definitely gotten used to technology just working.
We expect it, right? We expect it to magically turn a fluctuating temperature into a neat little number on a display, or a button press into a perfectly timed command that moves, say, a robotic arm.
But it's not magic.
No, absolutely not.
Yeah.
It's the result of incredibly painstaking, really intricate engineering. And as our source today points out, that specific engineering know-how, that critical knowledge, well, it might actually be at risk of being lost.
Which is a pretty serious thought.
It really is. Okay, so let's unpack this a bit. Today we're doing a deep dive into some really compelling insights from William L. Weaver's piece, Mind the Gap in the JPL Stack. And it's an explanation that honestly goes way beyond just talking about programming languages.
Mm-hmm.
Weaver argues that three seemingly separate technologies, JavaScript, Python, and LabVIEW, they aren't just tools. He sees them as like foundational pillars for bridging this really critical physical-digital divide.
Especially now as we move into this era of smarter, more autonomous systems.
Exactly. So this isn't just about understanding a bit of code here and there. It's about a fundamental shift in how we think about, build, and interact with technology itself. And maybe most importantly, it's about preserving the knowledge we need to actually build the future.
And what's really fascinating here, something Weaver really emphasizes, is that this isn't just a technical problem. It's also fundamentally generational. It's rooted in how our whole tech landscape has evolved.
Ah, okay.
Yeah, he highlights this potential kind of silent erosion of expertise, an erosion that could genuinely hold back future innovation if we don't, tackle it head on.
So what's the plan for today's dive?
Well, we're going to journey back a bit, understand the origins of this gap. Then we'll look closely at three pretty pivotal technological revolutions that actually, while being hugely successful, kind of inadvertently helped widen that gap.
Okay, the unintended consequences.
Precisely. And finally, we'll explore Weaver's vision for how these exact same technologies are now being synthesized, brought together intelligently to forge a new kind of technologist, what he calls the solution architects of tomorrow.
Solution architects. I like that. It's a really comprehensive journey then from the gritty, low-level hardware stuff where every single bit mattered,
Oh, yeah.
all the way up to the polished, super intuitive user interfaces that we just completely take for granted now.
Exactly. And it all starts with what Weaver calls, quite poetically, I think, the lost art of the digital craftsman.
The lost art with the digital craftsman. Okay, let's go there. To really get a feel for this lost art, we kind of need to wind the clock back, right? Back to say, the 80s and 90s.
That's the period.
This was this vibrant but often really challenging era of the digital craftsman. If you were an engineer or maybe a scientist back then and your job was to make a computer, talk to the real world.
Which was not a trivial thing.
Not at all. Whether that meant measuring something physical super accurately or controlling some mechanical system with precision, Weaver calls it a high Gothic art form.
That's a great description. High Gothic art form. It captures the complexity.
It really does, because it wasn't just about downloading an app or plugging in some pre-made USB sensor like today. No, this was way deeper, a much more fundamental kind of engagement with the machines themselves.
It was about building the connection yourself.
Yeah, meticulously crafting, like byte by byte, the actual communication pathways between the abstract digital logic inside the computer and the tangible reality of the physical universe outside it.
And it's so important to understand just how hands-on, how manual this process really was. The source paints this vivid picture, almost tactile, of engineers speaking what it calls these esoteric dialects of the machine.
Esoteric dialects, love it.
Yeah. And we're not talking high-level human-friendly code here. We're talking languages like Fortran, often confined to those structured columns, maybe on punch cards early on or green screens later, mainly for heavy number crunching, simulations, that kind of thing.
Right. Big science.
Big science, yeah. Then you had Forth, highly unconventional, very stack-based. It gave you this almost immediate direct line to the hardware.
Really? Direct control.
Oh, yeah. Minimalist, super powerful, and incredibly immediate. You could fiddle with specific memory addresses, hardware registers with this startling precision.
Wow.
And then, of course, you had ANSIC, known for its, well, unforgiving precision, its raw power. Every single byte, every memory allocation really, really mattered. Mistakes were costly, often led to these mysterious crashes or just weird, unpredictable system behavior.
So these weren't just programming languages in the abstract sense.
Not at all. They were the actual levers and pulleys, the tools you use to directly manipulate the flow of electrons, the logic signals right inside the hardware.
That's incredible. So just to do something seemingly basic today, like measuring a voltage from a sensor, or maybe sending a command to turn a little motor,
Uh-huh.
you weren't just writing a few lines of code calling some high-level function. You were, as Weaver puts it, manually orchestrating a delicate conversation between a physical transducer and a digital processor.
That phrase, delicate conversation, is perfect.
It is, isn't it? And maybe we should clarify transducer for everyone. Basically, think of it as that crucial bridge, right? Between the physical thing you're measuring, temperature, pressure, light, whatever, and the electrical world. It converts the physical into a measurable electrical signal.
Right. And then your code, your painstakingly crafted code,
Mhm.
had to take that raw, often messy, noisy electrical signal,
Mhm.
filter it, calibrate it, maybe amplify it, and somehow transform it into clean, usable digital information the computer could actually understand.
And the meticulous nature of this, Weaver really emphasizes this. It just can't be overstated. He describes it so well. Each line of code was a carefully placed wire, each memory buffer a hand-carved gear.
Wow. That paints a picture.
Doesn't it? You needed this really intimate understanding of like the precise timing of electrical pulses, the specific quirky characteristics of different sensors, the exact memory addresses where your data had to be stored and fetched from.
It sounds like building a complex miniature clockwork mechanism.
Yeah,
By hand.
exactly. Where just the tiniest mistake, a single misplaced instruction could throw the whole thing into chaos. You'd get wrong readings or the system would just crash entirely.
No undo button for a mental miswiring.
Precisely. And this inherent difficulty, this complexity, that's exactly why it was, as Weaver says, difficult, demanding, and accessible only to a dedicated few.
Yeah, this wasn't something you could just pick up from a weekend workshop or an online tutorial.
No way.
It required years of focused study, loads of hands-on trial and error, and this deep, almost intuitive grasp of both physics, classical physics, and the real nitty-gritty of digital logic design.
But in wrestling with that difficulty, those digital craftsmen, they learned something profound.
They really did. They forged this invaluable truth that the boundary, that interface between the physical and digital worlds, it's a place of immense complexity and nuance.
And this wasn't just theory from a book.
No, this was hard-won wisdom, earned through countless hours debugging stubborn code, painstakingly calibrating sensors that drifted, staring at oscilloscope screens, watching those dancing
He's
waveforms.
trying to make sense of it all.
Yeah, trying to coax predictable, reliable behavior out of inherently unpredictable physical reality.
Mm-hmm.
They really got the physics of data in a way that's perhaps less common now.
Okay, so let's fast forward to today, our present digital reality. And that boundary, that frontier Weaver talks about, the one with all that complexity and nuance. Well, it feels like it's been almost entirely abstracted into oblivion.
That's a strong phrase, but it feels accurate in many ways.
Think about it. The app-native generation, basically anyone who's grown up with smartphones, tablets, smart speakers everywhere, they live in a world that feels, well, flawlessly seamless.
Interfaces just work.
Right. You tap an icon, something happens instantly, almost like magic in the real world. Your lights dim, your thermostat adjusts, your car unlocks, poof.
The expectation is seamlessness.
Totally. This generation expects the digital world to just work perfectly, respond instantly, predictably, without any real thought about the mechanics underneath it all. But, as Weaver points out, they often lack that firsthand experience with what he calls the physics of data.
And that's not just some academic idea.
No, it's the raw, messy, analog reality of how you actually accurately, reliably translate something like, say, temperature, which is continuous, it fluctuates, or pressure changes, or light intensity. How you turn that into clean, discrete, structured, trustworthy digital information that a computer can actually process and understand.
Right, like measuring boiling water. It's not one neat number.
Exactly. It's constantly changing, right? Affected by air currents, stirring the pot itself, turning that noisy, continuous physical reality into a clean digital number a computer can trust without losing key info or adding errors from sampling or quantization or just environmental noise
Hmm?
that's grappling with the physics of data.
When it's a profound disconnect from the messy truth of data acquisition for many people today.
Yeah, and this is precisely where Weaver's gap really emerges, isn't it?
Absolutely. As that generation of digital craftsmen, the folks who really understood that physical-digital boundary, who knew how to wrestle with noise and calibrate signals right down at the lowest levels as they start to retire,
Mm.
a critical body of knowledge is at risk of being lost. And this isn't just, nostalgia for old programming languages.
No, it's more fundamental.
It is. It's about potentially losing the fundamental understanding of how to reliably get accurate data from the real world in the first place,
Yeah.
how to robustly control physical systems based on that data,
Ah.
and crucially, how to troubleshoot the inevitable, often really subtle problems that crop up right at that critical physical-digital interface.
And without that expertise.
We risk building systems that are brilliant, digitally speaking, but fragile or unreliable when they actually have to interact with the real world.
Okay, this is where it gets, honestly, it feels really interesting and maybe a bit urgent. The potential impact of losing this knowledge, it feels significant.
It could be, yeah.
Imagine a future, right? We've got these brilliant data scientists, cutting-edge AI gurus doing amazing analysis and prediction, but hardly anyone left who truly understands how to reliably get the raw, trustworthy data into the machine to begin with.
Or how to translate the AI's complex decisions back into safe, precise actions in the physical world.
Exactly. It's like having the world's best chef. But nobody in the entire food system knows how to actually grow the vegetables, harvest them properly, or even transport them safely to the kitchen.
That's a great analogy. The raw ingredients are missing, or at least the understanding of them.
Yeah. And that's the strategic problem Weaver is pointing to. It puts us at this critical crossroads, right? For educators training the next generation and for industry leaders building what comes next.
It really frames the challenge.
So we've identified this gap, this knowledge possibly fading away, but to really get how we got here, and more importantly, how we might bridge it, we need to look at these three parallel tech revolutions. Each one was hugely successful, totally transformative, but each, maybe unintentionally, contributed to this growing abstraction, pushing that physical-digital frontier further out of sight.
And these are the rises of Python, LabVIEW, and JavaScript. Sort of independent, but intertwined.
Right. Let's start with Python, a language that, maybe more than any other, just fundamentally changed developer productivity across so many fields.
So absolutely, its impact is huge.
And its emergence, Weaver points out, wasn't just random luck. It was a direct and pretty elegant answer to what he calls a long-standing schism in the programming world, a tension that had bugged developers for ages.
Yeah, for years, programmers often faced this really agonizing choice, almost binary, when they started a project.
What was the choice?
Well, on one side, you had these really powerful but kind of daunting languages like C++.
And C++F, still widely used, right?
Oh, yeah, definitely. And C++ offered and still offers absolute control over the hardware. A level of granular manipulation that was, frankly, unmatched. Great if you were building, say, operating systems or high-performance computing stuff, or complex game engines where every millisecond, every byte counts.
Maximum performance?
Maximum performance. But that power came with a hefty price tag. Immense complexity and notoriously slow development cycles.
The trade-off.
Exactly. Writing really solid, bug-free C++ is hard work. It's prone to subtle errors, memory leaks, requires meticulous attention. Developers spend a ton of time just managing memory, dealing with pointers, low-level system stuff, tasks that could just drain development time.
Okay, so C++ is powerful but complex and slow to develop in. What was the other side of this schism?
On the other side, you had languages like Java. Java took a very different approach.
Yeah.
It prioritized safety and cross-platform stability.
Right. Write once, run anywhere.
That was the promise, yeah.
Yeah.
And it made Java incredibly popular for large corporate teams building big enterprise applications that needed to run consistently everywhere.
Makes sense.
But while Java delivered on safety and portability, it often got criticized for being rigid in structure and excessively verbose.
Verbose means you have to write a lot of code.
Yeah, often you had to write quite a bit of boilerplate code, sort of setup stuff, just to do relatively simple things. And its strict, object-oriented style, while powerful for organization, could sometimes feel a bit restrictive, less agile for getting things done quickly.
So C++ for power, Java for safety and portability, but both had significant drawbacks in terms of developer effort or flexibility.
That's a good summary. And then Python emerged as what Weaver calls this third way, a really elegant solution that kind of sidestepped those rigid choices.
How did you do that?
Python didn't try to match the low-level control of C++ or the really structured, verbose style of Java. Instead, Python made a strategic bet. It decided to optimize for the most valuable resource of all, human development time.
Ah, focus on the programmer, not just the machine.
Precisely. Its core philosophy was about making programming itself faster, easier, more enjoyable. It achieved this by being simpler to write than C++ and far less verbose than Java. Developers found they could express complex ideas with way fewer lines of code. It reduced the mental load, sped up the whole process.
And this simplicity, this focus on efficiency for the human, that made it perfect for certain groups.
Absolutely. As Weaver notes, it was the perfect fit for scientists and engineers. Why? Because their main goal, typically, was not programming, but getting an answer.
Right, they're using the computer as a tool for their science or engineering work.
Exactly. They weren't usually trying to build a new OS or a huge corporate system. They needed to process massive data sets from experiments, simulate complex physical things, automate analyses. Python, with its clean syntax and amazing libraries like NumPy for numbers, SciPy for science stuff, Pandas for data handling. It let them focus on the core problem, not get bogged down in software development details.
So it democratized powerful computing for them.
Hugely. It enabled breakthroughs at a much faster pace. But, and here's the connection to the gap Weaver talks about, this very elegance, this abstraction, away from things like manual memory management or low-level data types.
Yeah.
It subtly encouraged a whole generation to focus just on the high-level logic.
Making the underlying hardware interaction less visible.
Exactly. Inadvertently widening that chasm between the analytical software they were writing and the raw hardware interaction that actually produced their data in the first place.
Okay, so that's Python revolutionizing developer productivity and data analysis. What about the other revolutions happening around the same time?
Well, while Python was taking off for general development, a parallel and just as transformative, revolution was happening quietly in the more specialized world of scientific and industrial measurement and control, instrumentation.
Okay.
This was spearheaded by National Instruments.
Hmm.
And it started apparently with this really insightful, almost philosophical question their engineers asked themselves. Why must we force scientists to think like computer scientists?
That is a brilliant question. Why impose one way of thinking on another?
Exactly. Because what they saw was something fundamental. Engineers and scientists across all sorts of fields already had a universal visual language for thinking about and designing systems.
You mean like diagrams?
Yeah. They were already using block diagrams and flowcharts on whiteboards, in notebooks, just in their heads, to visualize processes, how data flowed, the logic of a system. The truly revolutionary idea behind LabVIEW, which stands for Laboratory Virtual Instrument Engineering Workbench, was to take that existing way of thinking and literally make the diagram itself the program.
Whoa, okay, wait. Make the diagram the program? That's a total departure from typing text code.
Completely radical. Instead of writing line after line of, sometimes cryptic text code, you could now visually connect function blocks together on a screen. You literally drew your program by wiring components together.
That sounds incredibly intuitive, especially for visually oriented people like engineers often are.
It was. This whole new graphical programming language, which they cleverly called G, was built specifically, optimized purely for scientific productivity. And it dramatically empowered a huge range of domain experts, chemists, physicists, mechanical engineers, you name it, to automate their own experiments, build custom measurement setups, develop complex control systems.
So it lowered the barrier to entry for automation.
Massively. What LabVIEW did essentially was abstract away the really painful, low-level complexity of hardware drivers and timing. That had always been a huge barrier. Before LabVIEW, if you wanted to connect some specialized sensor to a computer and get reliable data,
you were writing low-level C code.
Often, yeah. Talking directly to hardware registers, managing tricky interrupt routines, handling precise timing. It was tough. LabVIEW gave you these pre-built graphical blocks, these intuitive icons that wrapped up all those low-level interactions. It made sophisticated data acquisition and control accessible, even if you didn't have a deep computer science background.
So a biochemist could focus on the biochemistry, not the data acquisition card programming.
Exactly. They could focus on their reaction, not how to read the temperature sensor correctly. But Weaver argues, while LabVIEW was brilliant at lowering this barrier, its very graphical nature, by design, removed the need for users to understand those textual command line type interactions that forced earlier engineers to grapple with the granular hardware logic.
So even as it empowered people, it also contributed to the abstraction.
In its own way, yes, a subtle but significant contribution to that overall abstraction, making the lowest levels less visible, even as it made automation vastly more accessible.
Okay, so Python for developer productivity and analysis, LabVIEW for scientific productivity and instrumentation. What was the third revolution?
The third, happening right alongside these, was focused squarely on the user, on the human experience of interacting with digital systems. The incredible rise of JavaScript.
Ah, JavaScript, the language of the web, essentially.
Pretty much. Think back to the very early days of the World Wide Web. Web pages then were, well, incredibly basic by today's standards. Mostly just static documents.
Like online brochures.
Exactly. Digital brochures, online newspapers. You could read stuff, scroll, click hyperlinks to go to other static pages. But you couldn't really do much interactively on the page itself.
Right, no dynamic stuff.
No. But people quickly realized they needed interactivity. They wanted buttons that actually did something when clicked, forms that could check your input before sending it off, elements changing on the page without that jarring full-page reload. That fundamental need gave birth to JavaScript.
And its origin story is pretty wild, isn't it?
Legendary. Almost unbelievable. It was initially created in just 10 days at Netscape, the browser company that was dominant back then.
10 days for a language that runs basically everything now.
10 days. Its first goal was actually pretty simple.
Yeah.
Be a simple scripting language to add some life, some dynamism, directly into web pages within the browser itself, to allow for those smoother user experiences without constantly hitting the server and reloading everything.
But then web applications got way more complicated.
Exponentially more complicated.
Yeah.
Moving from simple forms to really rich dynamic interfaces. Think early social media, online maps. Managing the user interface became, as the source puts it, a monumental task.
Why was it so hard?
Developers just found themselves drowning in increasingly tangled, unmaintainable code. People often called it spaghetti code, because changing one little thing over here
would break something completely unrelated over there.
Exactly. Everything was so interconnected and messy. Debugging was an absolute nightmare. It was slowing down web development massively.
So how did they solve that?
Well, this challenge was really elegantly tackled by the rise of modern JavaScript frameworks. The big ones being React, which came out of Facebook, and Vue.js, created by an ex-Google engineer.
React and Vue. Still huge today.
Absolutely dominant, and they brought this completely new, really powerful way of thinking about building user interfaces. The idea of reusable stateful components.
Okay, break that down. Reusable stateful component.
Instead of thinking of a whole web page as one giant lump of code, you started thinking of it as a collection of smaller, independent, self-contained building blocks, modular units.
Like Lego bricks for interfaces.
Kind of, yeah. Each component, maybe a button, the navigation bar, a search box, a specific input field, had its own logic, its own look, and crucially, its own internal state.
And stateful means it remembers things.
Exactly. Think of a simple login form. Each input field, username, password, is a component. It's stateful because it needs to remember what you typed into it, right? That typed text is part of its internal state.
Okay, got it.
If you type something, delete it, type something else, the component state keeps updating. Then maybe you click submit, and its state changes again. Perhaps it shows a loading spinner or later an error message. These frameworks make managing all those little mini memories, those states across maybe hundreds of components on a complex page, way easier and more predictable. It avoids the spaghetti code nightmare.
And the result of this component-based approach?
Truly transformative. Developers could now build these incredibly complex, data-driven applications efficiently, scalably, and importantly, these apps could run smoothly on any screen, from a desktop browser to a mobile phone or even a smart TV. It really turned the web from static documents into this dynamic, interactive, truly ubiquitous platform.
But connecting this back to Weaver's gap, JavaScript's success also played a role.
Weaver highlights that its phenomenal success in creating these seamless, really effortless user experiences further cemented that expectation of magic. It pushed the messy reality of the physical interface, the stuff LabVIEW is dealing with, even further out of sight for the typical user, the app-native generation. It fostered this maybe false sense of simplicity across the whole tech stack.
Okay, so let's tie these threads together. We have these three hugely successful technologies.
Python for analysis and general programming, with its massive library ecosystem.
LabVIEW for instrumentation, data acquisition, scientific productivity through visual programming.
And JavaScript for the dynamic user interfaces, the web experience.
Each became, as you said, undisputed leaders in their respective domains. They each solved a really important problem, pushed innovation forward like crazy.
No question about their individual success.
However, and this is the crucial, almost ironic twist, Weaver points out, their very success, their amazing ability to simplify things, to abstract away the complexity.
Also deepen the abstraction.
Right. Every new layer of ease, every boost in power, every helpful framework, it inadvertently moved both users and developers further away from the underlying hardware, further from that tangible, sometimes difficult, physical, digital interface.
Creating this generation that's incredibly skilled, brilliant even, within the digital realm, but maybe less intimately connected to, less understanding of the raw, often messy physical reality that actually generates the data or receives the commands in the first place.
And this leads us right to what Weaver calls this profound strategic crossroads. He basically puts a critical question to all of us educators, industry leaders.
A really fundamental question.
Yeah. Do we allow the fundamental knowledge of the physical-digital interface to atrophy, to just fade away? Or do we find a modern way to teach it, to actively bridge this widening gap?
So what does this all mean? What's the path forward for building systems that reliably interact with the physical world?
This is where Weaver's argument gets really interesting and maybe a bit unexpected. He argues the answer isn't about trying to turn back time, right? Not about lamenting what's lost or forcing everyone back to those super low-level methods of the old digital craftsmen.
Okay, so not going backwards.
No, quite the opposite. He proposes that the synthesis of these very tools is the modern bridge, combining them intelligently. He doesn't see this combination as some kind of nostalgic throwback. He sees it as a vital tool for the future, precisely because this combination has the unique ability to make the invisible visible again.
So using the tools that created the abstraction to now reveal what's underneath.
Exactly. It's about cleverly combining their individual strengths to get this synergy, the best of all worlds. The power of understanding low-level interaction combined with high-level analysis and intuitive user interfaces.
And central to this synthesis, perhaps surprisingly for some, he places LabVIEW.
Right. How does LabVIEW, with its very unique graphical approach, become this orchestrator, this modern bridge? How does it help reintroduce that physics of data idea to a new generation?
Well, Weaver explains that LabVIEW's core graphical data flow paradigm allows a new generation to visually construct the very interface their predecessors had to painstakingly code in lines of text.
So instead of abstract code,
you see these intuitive graphical blocks connected by wires that literally show the flow of data. You can actually see the data flowing as it happens, maybe from a sensor through a timing loop to an analysis function. This visual representation is incredibly powerful, not just for building things, but crucially, for learning. Gives you immediate, tangible feedback.
So it makes those abstract ideas, data flow, system interaction, really concrete, visible, like an interactive blueprint.
Exactly like that. And it directly teaches fundamental concepts, things like determinism, that guarantee that a program will behave predictably, repeatably, every single time it runs, which is critical for measurement and control.
Okay, determinism. What else?
Parallelism, the ability to run multiple tasks simultaneously without them interfering with each other. Vital for complex, real-time systems. And maybe most importantly, hardware integration.
Yeah.
The actual art and science of making software reliably talk to and control physical devices.
And these aren't learned just from a book.
No, they're learned as tangible, interactive practice. You literally drag a block that represents, say, temperature sensor onto your diagram. You connect it with a wire to a block that processes the measurement, and you see the data flowing in real time, maybe onto a graph on the screen. This hands-on visual way of working directly tackles that experiential gap in understanding the physics of data that the app-native generation might have.
Okay, that makes a lot of sense. But a question definitely comes up here. If LabVIEW is so powerful and visual for acquiring data for instrumentation, why not just do all the analysis right there in LabVIEW?
That's a very natural question.
Yeah, why, as Weaver acknowledges, would you deliberately hand off the analysis when LabVIEW itself has powerful libraries for doing calculations and stuff? It seems like an extra step.
It does seem counterintuitive at first, but this brings up a really critical point, and Weaver offers what he calls a simple truth to explain this division of labor. The entire global engine of modern artificial intelligence and specialized data science is built on Python.
Ah, the ecosystem argument.
Precisely. While LabVIEW does have capable tools for data processing and analysis, it just cannot possibly compete with the sheer scale, the breadth, the depth, and especially the incredibly rapid evolution of Python's open source ecosystem.
Can you give some examples?
Sure. Think about the absolute cutting-edge algorithms being developed constantly in frameworks like TensorFlow and PyTorch. These are the foundations of modern deep learning, AI, or the vast statistical toolsets you find in Python libraries like SciPy and stats models. Or think about the countless highly specialized niche libraries built specifically for things like genomics or astrophysics or advanced materials science or complex financial modeling.
All happening primarily in Python.
Overwhelmingly. These incredibly powerful, constantly evolving tools were all born and refined in Python's open source ecosystem. They benefit from this massive global community of brilliant researchers and developers who are just continually pushing the boundaries of data science and AI.
So it's like this huge collaborative global brain trust, all focused on Python for these really intense analytical tasks.
Exactly. And Weaver uses this brilliant analogy. A wise craftsman, he says, does not insist on forging every tool. They build the perfect workshop and know when to reach for the revolutionary instrument someone else has perfected.
I like that. Build the workshop, use the best tools available.
Right. So LabVIEW's role in this synthesized model is strategically defined. Its job is not to recreate this ocean of innovation that Python represents. Its job is to provide the most reliable and robust connection to it.
Okay, so LabVIEW focuses on what it does best.
Interfacing with that complex, sometimes ambiguous physical world, acquiring clean, trustworthy data, controlling physical systems precisely, and then it seamlessly passes that high-quality, well-structured data over to Python.
Which in turn excels at the heavy lifting.
Exactly. Python excels at the complex computation, the advanced statistics, deploying those cutting-edge AI algorithms. It takes the pristine data LabVIEW provides and works its magic.
That sounds like a really smart, powerful partnership. This integrated model, this deliberate synthesis, Weaver calls it a powerful and necessary division of labor.
He does, and he takes the analogy even further, suggesting that this division mirrors the most important collaboration of our time, that of the human and artificial intelligence.
Wow, that's a big statement. LabVIEW and Python mirroring human-AI collaboration. How so?
Well, in this model, he suggests LabVIEW serves the role of the human in the loop for the system. Think of it as the intelligent orchestrator, the part that provides context, gives purpose, skillfully manages the ambiguities and unpredictabilities of the physical world.
So it's the part that understands the real-world constraints.
Exactly. The subtle nuances of different sensors, the critical timing needs of physical events, the importance of human oversight, intervention, intuitive interaction. It's focused on efficiently getting clean, reliable, contextualized data out of that messy physical reality.
Okay, LabVIEW as the human in the loop managing the physical interface. And then Python.
Then, once that data is meticulously acquired, cleaned up, prepared by LabVIEW, Python in turn acts as the efficient and powerful AI, executing its complex computational tasks on the clean, well-structured data it is given.
So LabVIEW bridges the analog to digital gap, ensures data quality, and Python takes that high-fidelity data and runs the complex algorithms, making predictions, finding insights, spotting patterns, maybe even driving sophisticated control strategies based on the analysis.
Spot on. And the absolute critical takeaway here is that neither replaces the other. They work in synergy to create intelligent systems far more capable than the sum of their parts. This collaboration, leveraging the unique strengths of each tool rather than trying to force one tool to do everything, that's the core of Weaver's argument for the future.
Intelligent specialization, seamless integration.
Leading to systems that are not just powerful, but also robust, understandable, and ultimately manageable.
Okay, so we've traced this journey, the lost art of the craftsman, the gap, the three revolutions that paradoxically widened it, and now Weaver's proposed synthesis using those same tools, LabVIEW, Python, to bridge it. But why is this all so critical now? Why the urgency? Especially as we're looking at a future with more and more intelligent autonomous systems.
Weaver is really clear on this point. He states bluntly, We cannot afford to raise a generation of scientists and engineers who are brilliant at analyzing data, but have no idea how to acquire it reliably or how to implement their insights back into the physical world. We absolutely must, he says, mind the gap.
Mind the gap. It's not just a title, it's an imperative.
It really is.
Right.
And it raises a broader question, too. What are we really teaching? Or rather, who are we really cultivating when we educate students to build these kinds of integrated systems?
Right. It's more than just learning software X and software Y.
Much more. Weaver argues we're actually teaching them how to be the true solution architects of the future. These are the leaders, he thinks, who will build the bridge between the world of bits and the world of atoms. The people who truly understand the entire life cycle of data from its raw physical origin all the way through analysis to presentation in action.
A truly holistic, full-stack view of intelligent systems.
Exactly.
And this bridge, this complete picture, it isn't really complete without that final, crucial link back to the person using the system, right?
Absolutely critical. When these complex intelligent systems may be monitoring a power plant, analyzing medical scans, controlling a factory robot when they need to actually present their findings or allow a human to interact, perhaps on a web dashboard you can access from anywhere. Weaver points out, it is the world of JavaScript that provides the final crucial link to the human. That's the user-facing window.
So the complete skill set, the full knowledge base for this solution architect becomes really clear and integrated.
It does. You need LabVIEW for that direct physical world interaction. The data acquisition, the actuator control, that robust connection to reality.
A physical layer.
Then you absolutely need Python for the heavy analytical lifting, the complex math, the AI, the deep data science that turns raw data into real insight.
The analytical layer.
And finally, you need JavaScript for that presentation layer, building those intuitive user interfaces, the dynamic dashboards, making sure those hard-won insights are accessible, understandable, and actionable for the human user, no matter what device they're using.
The presentation layer, physical, analytical presentation, LabVIEW, Python, JavaScript.
That's the stack.
Wow, you've really brought that full circle. It's not just about collecting technical skills like badges. It's about fostering this holistic, integrated understanding, a complete picture of how these complex intelligent systems work, from the ground up right to the user screen.
And that kind of comprehensive knowledge isn't just nice to have. Weaver argues it's absolutely essential for the next wave of innovation. It ensures we're not just abstracting problems away, but actually solving them with a full grasp of their physical and digital dimensions.
It's almost poetic, isn't it? How the very tools that simplified things and maybe created this gap are now, when used together, the key to bridging it.
It's a fascinating turn.
So what we've really unpacked today, diving into William L. Weaver's Mind the Gap in the JPL stack, is how this combined power, the synergy of LabVIEW, Python, and JavaScript, isn't just about using tools. It's a vital, intelligent strategy for actively bridging that critical generational knowledge gap.
It really provides a blueprint, doesn't it, for creating systems that are not just intelligent, but also robust, reliable, and intuitive in how they interact with our complex physical world.
And hopefully this understanding empowers you, our listener, to be a more informed participant in this tech-driven world we all live in, whether you're actually building these systems or just interacting with them daily.
Which we all are, constantly.
Right. Recognizing these hidden layers from the raw sensor through the analytical processing to the polished interface, it gives you, I think, a much deeper appreciation for the sheer complexity and ingenuity involved in making the world of bits and the world of atoms work together so smoothly.
Absolutely.
And maybe, as you go about your day now, you'll start to notice just how many unseen layers of tech are humming away behind every seemingly simple interaction. That smart thermostat reading the room temperature, the self-driving car navigating traffic. These intricate conversations are happening constantly between the physical and the digital.
Below the surface.
Yeah. Understanding those layers, thinking a bit like a solution architect, it really opens up a whole new perspective on our engineered world. And it makes you wonder, doesn't it? What other gaps might exist in our understanding, maybe in other fields, and what other amazing bridges are just out there waiting for us to imagine and build.